Let's see here. Let me begin with a word of prayer. So I will start. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students in this class. Just ask you to be with us, help us to glorify you what we do, and understand a little bit more about your creation. Lord, in your name I pray, Lord Jesus. Amen. All right, so there was a question about air brakes, I guess, or air friction. And so I'll deal with that question here momentarily. There's not much to say there, really. So if you're just solving a velocity-dependent friction problem, and you're talking about like a object falling or something, right? So here's the deal, right? You've got your force of friction, let's say it's falling, right? So force of friction goes up, gravity goes down, right? And your formula for the motion is mass times acceleration is what? It's, force of friction, which is whatever that is, minus mg, right? And so the question asks you, what's the terminal velocity? So, all right, so like for that, I think in your homework, this is something like, beta v cubed or some such thing, right? So to directly solve that would be kind of a drag, pun intended. So, you're welcome. So this would be m dv dt equals to beta v cubed minus mg, right? So I don't really want to try to solve that. It's kind of horrible, right? Separate and integrate. I mean, you could try, but then you'd be up against the integral of 1 over a cubic, right? Not my favorite integral, unless somebody's paying me. So you don't really want to solve this directly. So here we can use a conceptual approach. Let's think about it. If we're looking for the terminal velocity, what happens with the terminal velocity? Like if you jump out of a plane and you're falling, do you keep just going faster and faster and faster? No, you reach a certain terminal velocity. What's characteristic of that? You're not speeding up anymore. What's your acceleration when you reach this? Your acceleration 0. So to find the terminal velocity, we can just set this equal to 0 for terminal velocity. And if I say anything more, I think I've solved the homework problem. But that's pretty much it. So you don't actually have to solve the velocity as a function of time. We can use this simple conceptual device to find terminal velocity. Yeah.
Referencing the homework problem, it has the force of air friction as negative. If that's negative, would that make mg positive?
Whatever equation you write down, it should be physically reasonable. So I think this is physically reasonable because the, let me think about my equation for a second here. So I think in the problem, I'm given that that's minus beta v cubed, right? So I definitely need the minus in what I'm writing up here, so thank you. Now it makes sense because v is negative, so that's positive, which makes sense, right? If v is negative, the force of friction should be up, right? The drag force shouldn't be like pushing your object down faster, right? It should be the opposite of gravity, yeah. So just because these both have minuses don't mean they're both pointing downward. See, v is negative, so you got a negative cubed. This is actually positive, given that v is negative in this situation. Taking v upward to be positive. There are other choices that could be made here. But other questions? So last time, we were talking about work. So I need to get back into that. So I'll remind you guys. We defined work, and let me just do a real simple pair of examples here to get us started. Example 1, suppose you've got a force which is like 10 newtons, 3 newtons, and minus 4 newtons applied from R1, which is, let's say, 0, 1, 2 in meters to R2, which is, let's say, 10, 10, 10 in meters, right? Find work done by F. Okay, so in this particular case, if you study the definition that I gave you last time, and you sort it out, you'll find that actually the work done here is simply the force dot the displacement. All right? So to calculate the work done, I can simply do work done is force dot displacement, right? Which here would be 10 newtons, 3 newtons, minus 4 newtons, dotted the displacement vector, which is what? Like 10 minus 0 is 10. Let's see here, 10 minus 1 is 9. 10 minus 2 is 8. All in meters, right? And so if I work that out, I've got myself 100 plus 270 minus 32. All of these guys have units of Newton meters. A Newton meter is an important unit. It also has another name. It's called a joule. A Newton meter is a joule. So whatever this is, what we got? 370 minus 32. What's that? 300, I hear 338. 338 joules. There you go. That's the work done by this constant force over this displacement. Yep.
Wouldn't it be 27?
Oh man, what did I do? Oh, rats. Thank you. Which is going to spoil the other thing too, isn't it? What we got? 95? Excellent. Thank you. So, in the case of a constant force, calculate the work done. We simply take the dot product of the force with the displacement. There's another very simple category of examples, which is if we have a work which is applied under one-dimensional motion. All right, so if we have a one-dimensional motion, it's also pretty simple. So, example 2, we can talk about the spring force. All right, the spring force is given by something called Hooke's law. Hooke was a contemporary of Newton who Newton didn't like for whatever reason. I think the reason was that Hooke was, which is kind of funny from given what I'm about to say, Hooke's work wasn't very mathematical, and Newton thought that physics should be mathematical, a fate which you're currently suffering, you know. And so anyway, Newton wrote this, Principia Mathematica, his giant work of physics, and he doesn't even mention Hooke in it, which is really kind of amazing given that Hooke was another sort of preeminent physicist of his time. So this is the spring force. This is called Hooke's law. The way this works, I'll think of it as being I'll think of it as being x. I'll think of x as being the horizontal position here, and so we've got like I'll draw it as if there's a mass attached to it because that's sort of most natural. So here, this would be x being less than 0. On the other hand, it might look like this, right? And this, so this distance, I'm trying to, same reference point here. I guess I should probably draw I usually draw the reference point to the middle of the mass. My bad. Sorry, guys. There we go. Middle of the mass. So there's my x. So here, so this is x greater than 0. This is x less than 0. Let me make both cases here. This is x equals to 0, all right? Does this formula make sense? Let's think about it for a second. If x is less than 0, then f equals to minus kx is what? Negative times negative. All right, k is a positive constant called the spring constant. So if x is less than 0, the spring is compressed and it pushes back that way. All right, that's why that makes sense. On the other hand, if the spring is stretched out, then the spring pulls on the mass to go back, right? And so that makes the force negative because it's leftward. So that's the reason for the minus, is to accomplish all these cases. If x is equal to 0, that means that the spring is in equilibrium position, so it's neither pulling nor pulling on the mass. All right? So we can calculate the work done in this case, right? So what's the work done? So let me show you how my Calculus 2 professor showed me this, and I think it's a good way. He's like, well, if you calculate the infinitesimal work done by the spring force, it would be minus kx dx. So the reason I need to think about that is that I can't just do force times distance because the force is variable, right? So but if I think about the little bit of work that's done moving the mass, moving the spring just a little smidgen dx at x, well, that gives me a little bit of work done then. And so if I want to find, work done, this is infinitesimally. So if we're going from x1 to x2, right, then we can find the work done in that situation by integrating from x1 to x2 of minus kx dx. And that will give me the work done by the spring force under such a displacement. All right? So what's that give me? Minus 1/2 kx squared. Fundamental theorem of calculus, this thing here. So I get 1/2 k times x1 squared minus x2 squared. All right? That's the work done by a spring under this motion. So a special case, like anytime we're talking about a one-dimensional force, and it's a variable force, to calculate the work done, we simply integrate. All right? Now if you study the general definition of work I gave last time, it does reduce to this in the context of a static one-dimensional force. If the force in one dimension is not time independent, if the force has like a time dependence to it, then this just integrating over position won't quite make sense anymore. But for a static force, we can do it. So in the notes I'm currently editing and will soon post, I have a footnote where I explicitly show you how this formula can be derived from the general integral that I wrote last time. But I'm not going to waste class time showing you that calculation because it doesn't matter that much. The example that I'm about to show you, though, I think should be interesting. So I want us to get back to a variable force. We'll keep it two-dimensional to keep it, not too complicated. And so this example will illustrate something we're up against with forces in two or more dimensions. I'm not sure this can really happen in one dimension, honestly, but certainly it's possible for 2 dimensions. So example 3, I'm going to look at the force, which is variable, and the formula for it's going to be x squared minus y for the x component and x plus y for the y component. All right? And what I want to do with this force is I want to calculate the work done by this force along a path and then along a different path. But these paths are going to be related. So let me draw you a picture of the paths I have in mind before I do any more calculations at all here. So here's the paths I have in mind. Pretty simple. They're both going to start at the point 0, 0. And they're both going to end at the point 1, 1. All right? However, they're going to be different paths. So we're going to look at this one that goes from 0, 0 over here to 1, 0. All right, I'm going to call that L1. And then I'm also going to look at, from here to here, this L2. All right. So it goes like here to here and then here to here. That's one path I'm going to consider. Another path I'm going to consider is the path that goes vertically from 0, 0 up here to 0, 1. All right? And I'm going to call this L3, and I'm going to call this one up here L4. All right? So I want to contrast the work done. I want to find work done over by F on like curve 1, which we're going to form by taking L1, then L2, and then curve 2, which we're going to let be curve line segment L3, then line segment L4. So this curve 1 and this curve 2, these are examples of what are called coterminal paths. All right, they have the same starting and the same ending points, right? The same initial point and the same terminal points. These are coterminal paths. So what do you think? Is the work done along the red curve going to be the same as the work done along the blue curve? What do you guys think? Yeah, maybe. Let's find out. So I'm going to give you parameterization for each one. So for R1, we can write a typical point here, all right, as x comma 0. Typical point over here has the form y comma 1. Typical point up here has the form x comma 1. Typical point over here has the form 0 comma y. So my R1 for L1 is going to be x comma 0. My R2 is going to be 1 comma y. My R3 is going to be 0 comma y. And my R4 is going to be x comma 1. All right? Then, if you like, we can calculate the infinitesimal displacements along each of these parameterizations, along each of these paths, in this sort of like natural fashion. Like, you guys tell me, what do you think these are going to be? I'll do the first one, you guys do the second one. So dr1 is going to be dx 0. Care to guess what dr2 is? 0 dy. Very good. This one? 0 dy again. This one? dx 0. Excellent. And so then I can calculate the work done along curve 1, right, as the integral from what? Well, the integral from over L1. Let me see here. I'm trying to think of how much detail I'm put down here. So integral from 0 to x. Excuse me, x goes from what? 0 to 1 here, right? Integral from 0 to 1 of f of what? I have to evaluate at R1, which is x0, and take the dot product with dr, which is dr1, which is dx0. Okay. Then plus the integral. So that's the L1 integral. Now the L2 integral, I'm integrating from 0 to 1 again. And this time I'm supposed to do f of 1y, dotted with my dr2, which is 0 dy. All right. So this is the integral from 0 to 1. Now what I have to do is I have to plug x and 0 into the formula for the force. All right. So I'm making a substitution here of x0 into the formula xy. So that is x squared minus 0, comma, x plus 0. dotted with dx0 plus the integral from 0 to 1 of, let's see here, so plugging in 1y into this, I get 1 squared minus y, comma 1 plus y. Dot product with my 0 dy. All right? So you can work these out. We'll do that. What do we got? Integral from 0 to 1. So 0 dot that is, so we just look at the x components, right? Like the x component's all that matters there. And the y component's all that matters in the other one, right? Which if you think about how we described work last time, it makes a lot of sense, right? Like the part of the force which is doing work, it's the part that aligns with the path, right? So only the x part aligns with L1, only the y part aligns with L2. That's why the dot products encode all that. So this with that, and this with that. The other piece is 0. So we have x squared dx plus the integral from 0 to 1 of 1 minus y dy, which by the way gives me 1/3 plus 1 minus 1/2, also known as 11/6. All right. So we have that. Why would it be 1 plus? Oh, did I do? Oh, yeah, thank you. Sorry, I'm getting carried away. I'm getting to the next part. So now that actually will be 11/6 because 5/6 plus 6/6 is 11/6. Now, next, let's calculate the work done along the other path. Right? So, guys, can I use example 1 or example 2 as a means of calculation here? Like I can't, right? Even though they're really simple paths that are lines, right? The force is variable. Yeah? So I have to deal with the actual definition of work here. I can't just, I mean, it ends up being integrals, right? But you have to kind of figure out what integral you're supposed to do. All right. So for the other path, we call it work 2. We're doing what? Integral, let's see here. So L3, we integrate from 0 to 1. F of what? Along the blue vertical piece, that's 0y, right? Plug in 0y into the force. I take the dot product with 0 dy. That's my dr3. Plus the integral from 0 to 1, as it happens, f of x comma 1, and I've got dx comma 0 for my differential there. Right? Now we have to plug in the formula for the path in question to calculate the work done by the force in question, right? So we have to mind where the force is because the force, it's a force field, right? It behaves different at different points. We have to evaluate the force field at the point in question. So, how does this work? Well, so you guys help me out here. We have f of, I can't see it yet. I gotta put my glasses on. It's sad. 0y, how's that work out for us? Remember the formula for f is over there? So we're supposed to do what? X squared, which is 0 squared, minus y, right? Comma, x plus y, which is 0 plus y, dot with 0 dy, plus the integral from 0 to 1. We do x squared minus 1, comma, x plus 1, dot product with dx0. Do these, what do we got? Integral from 0 to 1 of y dy, plus the integral from 0 to 1 of x squared minus 1 dx, right? Which these integrals are simply 1/2 plus 1/3 minus 1, also known as minus 1/6. So what's the deal here? Obviously, this is not equal to W1, right? So here's the definition, guys. F is path independent on U if for any pair of coterminal paths C1 and C2, the integral of C1 of f dot dr is equal to the integral of C2 of f dot dr. In other words, a path-independent force is one for which the work done between 2 points, it matters not which path you take between the 2 points. The work done is the same. All right? This is what it means to be path-independent. My example 3 is an example of a force which is what? It's path dependent. It's not path independent, right? It mattered whether we took the low path or the high. I mean, we took the red path or the blue path. They gave us different work, right? One was positive work, the one was negative work. These are quite clearly different. Yeah. So, any questions before I go on? Yes, sir.
What does it say between C1 and C2
Coterminal. Oh, this is an and. Sorry. Yeah. And by coterminal, I mean they like start and end at the same point, you know? Yeah.
When it says that is path independent on what's that?
U. On some set. So like path independence has to be understood relative to some domain. So we path independence where? All right. So the answer is path independent on U. Now usually we'll discuss path independence of a vector field with respect to its domain, you know. Here's another example I usually give. Example 4. We could look at f of x comma y equal to 1 over x squared plus y squared minus y comma x. Right? And see the unit circle. Right. Well, hey, let's say, forget the unit circle. Let's say the circle of radius r. So this one here, I might need to give you a little bit more. I mean, I think that the setup for this example 3 is not that tricky, really. This one I need to help you out a little bit. How do we, how do you parameterize a circle of radius r? So we do what? We have x equals to r cosine theta, let's say, and y is equal to r sine theta, right? That will parameterize the circle of radius r centered at the origin. So what I'm suggesting here is r of theta. I guess I should use time in here. I'm sorry, guys. I'll use time t. Time t. So this is a path that goes around the origin. What's the derivative? There's the velocity of the path, right? So let's calculate the force evaluated at the circle. What do we got? F of r of t. What are we looking at here? Let's take the dot product of that with the r dt. What do we get? So we're talking about 1 over, r squared cosine squared t plus r squared sine squared t for my denominator, right? My minus y is minus r sine t and r cosine t. So all I'm doing so far, guys, is just like plugging in the definition of my vector field here. I'm just plugging in these, right, into the x and the y formulas. Do you guys see it? Now I take the dot product with the velocity over here. I'll do it symbolically. The good news is the next step we're going to write, there's going to be like way less to write here. So what do we got? What's f here? F of r of t dot dr dt. How's that work out to actually here? So that's 1 over r squared, right? And there's an r squared from all this, right? And sine squared plus cosine squared. The r squareds, they be canceling. So this is just equal to 1. So to calculate the work done by this one around the unit circle, we have to do what? We just have to integrate from 0 to 2 pi dt. So the answer is 2 pi. I did all the work simplifying the integrand before I wrote the integral. I hope that's okay. Just organizing the calculation differently. This is a little bit weird, right? Why should the work done around the circle be 0? I mean 2 pi. Shouldn't it be 0? Should be, well, it's 2 pi. All right. So so these examples I'm giving you here, they're laying the groundwork for a discussion of what we call a conservative vector field. What is a conservative vector field? Well, let me tell you. So definition. A vector field, F, is conservative on U, all right, if there exists a potential function, I'm going to tell you what it is. It's a potential energy function, and I'll use phi for it here, such that. So here's the bad thing, guys. I don't know. I have worked myself into a stupid point. We need to change the names on some things to protect the innocent. Yeah, let me fix some things here. So U, I usually use the big letter U for potential energy. So you see how I've worked myself into a stupid corner here. So instead of saying U is the set, if you guys don't mind, you could just take U and cross it out and put like an S for like a space, if you like, a set. So S is some subset of the space we're talking about. S. So here, the context in which this is going on is S. S is the universe. And let's call the potential energy function U, because that's a pretty typical notation, such that F is equal to minus the gradient of U. So like this means, of course, as we talked about last time, like minus partial U, partial X, minus partial U, partial Y, minus partial U, partial Z if we're three-dimensional. This is minus the gradient. If there exists a potential energy function, then it's said to be a conservative vector field. All right. The triangle is for gradient. We defined it last class. So, and good question. So the point of this is probably best understood. I need to tell you a theorem of calculus for this to really be interesting. And the theorem is this. I'm going to say if f is equal to the gradient of little f. So this is like typically in calculus 3, we talk about the gradient of a function little f for the vector field big F. There's no minus in calculus 3 because in calculus 3, in the math world, we don't care about the minus because we don't care about energy. All right? So I'm going to state the theorem from calculus 3 and then we'll apply it here. But if f is the gradient of f and c goes from, say, point P1 to point P2, then the integral along c of f dot dr is equal to simply f of P2 minus f of P1. This right here is the so-called fundamental theorem of calculus for line integrals. All right? Fundamental theorem of calculus for line integrals. So corollary, all right? Corollary to this theorem is if f is conservative, right? And c goes from P1 to P2, then the integral of f dot dr is equal to what? Well, if it's conservative, that means the force is minus the gradient of the potential energy function. So this is the integral of minus the gradient of u dot dr over the curve. But I can pull the minus out, right? I can pull the minus out. And I can use the theorem. So that's u of P2 minus u of P1. But what did we say last time the line integral of the force is over the curve? What does this calculate? This calculates the work done by the force over the curve, right? So this is another way to calculate. So another way, this is, we can also say this minus the change in the potential energy, if you like. So here U is equal to PE, the potential energy. It's just minus the change in the potential energy is the work done by a conservative force. Work done by a conservative force. Now, all right. Well, this is cool. I mean, but if what did we prove last time? Last time we proved the work energy theorem. What did the work energy theorem say? You guys remember? No. I think what you said is right. Work energy theorem, but there was a precondition, right? If F is net force, right? If it's the net force, then what? The integral along the curve of F dot dr would be equal to like 1/2 m, let's say mv2 squared minus 1/2 m v1 squared, right? It was the so-called change in kinetic energy along the path. This is the work energy theorem. It only applies, of course, if the force we're talking about is the net force. All right? So what happens if we have the net force is a conservative force? Then we combine these two ideas, right? We get them both at once. And what does that mean? That means that the change in the kinetic energy is equal to minus the change in potential energy. And that is actually very interesting. Let me write it down. So putting these two ideas together, if my net force is in fact a conservative force, then I can write that this is equal to what? You know, let's say U minus U2 plus U1, right? Or of course, you could also call this change in kinetic energy K2 minus K1, just to write less. And so what do we got? We have K2 minus K1 equals to minus U2 plus U1. So what does this give us? This gives us that K1 plus U1 is equal to K2 plus U2, right? So this is what we call total mechanical energy. E1 is equal to total mechanical energy E2. This, my friends, is conservation of energy. Conservation of energy happens when the net force is a conservative force. Then we get this beautiful union between the work-energy theorem, which is a consequence of Newton's law, and the differential identities we looked at last time, paired together with the fundamental theorem of calculus for line integrals, which marries the gradient concept with the work integral. Put these two together, we have conservation of energy. Now, if the net force is not conservative, you don't get this, right? Like last time we looked at an example calculating the work done by friction, right? That's not going to be a conservative force. Why? So what do you guys think? If this formula is really special. If the force is conservative, what does that formula say? Let's really stop and meditate on this potential energy idea. So we have that the work done by a conservative force is equal to minus the change in potential energy. Does it care? Does it matter what the path is that connects points 1 and points 2? It does not, right? Think about it. There's no path dependence on the terminal points. It only depends on the difference in the value of the potential energy. Therefore, a conservative force is path independent. So we have a theorem. The following are equivalent. 1, F is equal to minus the gradient of U on S. All right. 2, F is path independent on S. 3, the integral around a loop of F dot dr is equal to 0 for any loop in S. And 4 is something I won't really, I'm going to mention it, but I wouldn't test on this because this is genuinely calculus 3 in the sense that like we don't really need it, but for the sake of completeness here, the curl of F is equal to 0 on S, and here adding condition S is simply connected. So you can kind of, for the most part, you can ignore part 4 here if you want, but for the sake of those of you who are possibly in Calc 3, I include it for the sake of logical completeness. Like we can check whether or not a vector field is conservative by calculating its so-called curl, and if it's non-zero, it's not a conservative vector field. Now, so how about my example 4? Well, my example 4, let's think about it. Do you guys understand why this can't be conservative? Suppose you had a potential energy function, right? Think about the circle, right? Pick a point. Call that point P1, which is also point P2. What's the change in potential energy around the circle, if it did have a potential energy function, what would you get? You get U of P1, U of P2 minus U of P1, right? The change of potential energy would be 0 because it's the same point starting and ending. So the change of potential energy, if there was a potential energy function there, would have to be 0. Yet we just calculated that the work done by that vector field around the circle is 2 pi, right? So because of this, this is not a conservative vector field. What's interesting about this one actually is that it actually fails. The curl of this is actually 0, but the tricky part here is what's the domain of this vector field? Like example 4, what's the domain of that vector field? It's the whole plane, right? But what do we have to take away? What's the one place that is not defined there? 0, right. The origin is not there. And if you take and delete the origin, the so-called punctured plane is an example of a set which is not simply connected. A simply connected set is one which you can take a loop and you can deform it to a point through a continuous morphing of that loop into a point. If I take a loop which encircles the origin here, like that, right? I can deform it down. But I will get stuck. On that origin. I can't get past the origin. I can't deform the loop to a point. For a space to be simply connected, you have to be able to deform the loop to a point without getting stuck on anything outside the space. That's the best non-technical definition I can give you for simply connected, but yeah. Any questions? So, listen. So now that we know we have vector fields which are conservative and those which are not, we can start using conservation of energy for conservative vector fields to solve problems. Because why? Kinetic energy involves velocity, which means we can go back, we can solve kinematic problems because this links together what? Velocity and also position for systems that have, potential energy. So our next order of business is to figure out, for these conservative vector fields, how do we actually calculate the potential energy for those, right? And then how do we use them to solve physical problems? That's where we're going. I'm still working on the notes, guys. I should hopefully have it soon. In the meantime, my lecture 15 is pretty complete. So anyway, thanks everybody.